Imagine for a moment an object so powerful it redefines our understanding of cosmic violence. A star with a magnetic field 1,000,000,000 times stronger than Earth's. A force so immense it could wipe your credit card from halfway to the moon. This isn't science fiction. This is the chilling reality of the universe's most magnetic monsters. Terrifying, right? These objects are called magnetars, and they are one of the most extreme and dangerous phenomena astronomers have ever discovered. To understand their power, we first need to understand what they are. At its core, a magnetar is a type of neutron star. But calling it just a neutron star is like calling a hurricane a gentle breeze. Their story begins with the death of a star far more massive than our Sun. When such a star exhausts its nuclear fuel, it can no longer support its own immense weight. Its core collapses catastrophically, triggering a spectacular supernova explosion that for a brief time can outshine an entire galaxy. While the outer layers are blasted into space, the core is crushed by gravity into an object of unimaginable density. This is a neutron star, a city-sized sphere, perhaps only 20 kilometers across, yet containing more mass than our Sun. A single teaspoon of its material would weigh billions of tons on Earth. But not every neutron star becomes a magnetar. For that, you need a special set of circumstances. Scientists believe that if the progenitor star was spinning incredibly fast before it died, that rapid rotation is conserved in the newly formed neutron star. This, combined with the turbulent, boiling motion of the super-dense electrically conductive plasma inside the young star, creates a powerful dynamo effect. It's like a cosmic electrical generator, but one that amplifies the star's magnetic field to almost incomprehensible levels. The result is a magnetic field of up to 1,000,000,000 Gauss. That's a 1 with 15 zeros after it. For comparison, a refrigerator magnet is about 50 Gauss. The Earth's magnetic field, which protects us from solar radiation, is about half a Gauss. A magnetar's field is 1,000 trillion times stronger. It is so powerful that it distorts the very atoms on the star's surface into thin, needle-like shapes. This colossal magnetic field is not static. It is constantly shifting and evolving, placing unimaginable stress on the star's solid crust, which is thought to be 1,000,000 times stronger than steel. The magnetic field lines that are anchored deep within the star twist and writhe, building up tension. Eventually, the strain becomes too much. The crust twists, and then, in a fraction of a second, it snaps. This is a starquake, a cataclysmic event that releases a burst of energy so profound it makes a supernova look tame. This energy is unleashed as a torrent of high-energy X-rays and gamma rays, the most energetic form of light in the universe. These are the infamous magnetar flares. They come in different sizes. Smaller, more frequent bursts are common, but occasionally, a magnetar unleashes a giant flare. These are among the most luminous events ever recorded. On December 27, 2004, humanity witnessed the power of such an event firsthand. A magnetar named SGR 180620, located nearly 50,000 light-years away on the other side of our galaxy, erupted. In just 1/5 of a second, it released more energy than our Sun has in the last 250,000 years. The initial blast of gamma rays was so powerful that it saturated the detectors of every gamma-ray satellite in orbit. Even from that immense distance, the flare slammed into Earth's night side, partially ionizing the upper atmosphere and disrupting some long-range radio communications. Think about that. An event that happened halfway across the Milky Way had a measurable physical effect on our own planet. It was a profound wake-up call for astronomers. This naturally leads to a frightening question. What would happen if a giant flare occurred much closer to home? The consequences would be catastrophic. A magnetar within a few hundred light-years could potentially trigger a mass extinction event. The initial wave of gamma and X-rays would be devastating. It would severely damage or destroy our ozone layer, exposing the surface to lethal levels of solar and cosmic radiation. It would strip atmospheres from planets, scramble satellites, and induce powerful currents in our power grids, causing a global blackout that could last for months or even years. Our technologically dependent civilization would be thrown back into the Dark Ages. The kill zone for a giant flare is estimated to be several dozen light-years. Any life-bearing planet within that range would be sterilized. But before you panic, it's crucial to add some perspective. Space is vast, and the known magnetars are all safely distant. The closest confirmed magnetar is thousands of light-years away, far outside the danger zone. Astronomers are constantly scanning the skies, and there is no evidence of a magnetar lurking in our cosmic neighborhood. So while the threat is theoretically real, it is not an immediate one. We are safe. So how do we study these invisible monsters? We can't see them with conventional telescopes because they are tiny and don't emit much visible light. Instead, we rely on a fleet of high-energy observatories in space, like NASA's Chandra, Swift, and Fermi telescopes. These instruments are our eyes on the high-energy universe, designed to detect the very X-rays and gamma rays that magnetars produce. Historically, magnetars were discovered as two separate classes of objects. Soft gamma repeaters, or SGRs, were sources that produced repeated, brief bursts of low-energy gamma rays. Anomalous X-ray pulsars, or AXPs, were slowly rotating neutron stars that were mysteriously brighter in X-rays than their rotation rate would suggest. It took years of observation and theoretical work to realize they were two faces of the same underlying object, the magnetar. Despite our progress, magnetars are still shrouded in mystery. We are grappling with fundamental questions. How exactly does the magnetic field decay over time? We know they are young objects, astronomically speaking, likely only active for about 10,000 years before their magnetic fields weaken and their violent outbursts cease. But the precise mechanism of this decay is a subject of intense debate, and there are even more tantalizing connections. In recent years, a new cosmic puzzle has emerged: fast radio bursts, or FRBs. These are incredibly powerful, millisecond-long bursts of radio waves from deep space. Their origin was a complete mystery until 2020, when a fast radio burst was detected coming from a magnetar within our own galaxy. This provided the first direct evidence linking at least some of these enigmatic signals to magnetars, opening a whole new window into their physics. It's a hypothesis that is rapidly gaining strength. From their violent births in the heart of supernovae to their cataclysmic starquakes and galaxy-spanning flares, magnetars represent the universe at its most extreme. They are natural particle accelerators, laboratories of physics far beyond anything we could ever hope to build on Earth. They challenge our theories of matter, gravity, and magnetism. They are a humbling reminder that even in the quiet darkness of space, there are forces of unimaginable power. While they pose no threat to us now, studying them teaches us about the fundamental laws that govern our cosmos. They are the universe's ultimate dangerous star magnets, and they still have many secrets left to reveal.